Welcome back. Thank you very much for all the help. We have gone through chapter 6 and 7. We talked about two new components, inductor and capacitors, in time domain, and we went into RL circuits and RC circuits, where we have only one storage element, and provided that the input is a DC excitation input, we were able to handle this using the same knowledge and material from pre-midterm, which was on nodal mesh, superposition, reductions, things like that, and handle it accordingly. But we are moving into chapter 9, and in chapter 9, the incoming signal is not DC. The incoming signal is an AC signal. An AC signal, a very friendly one of them, is going to be a sine cosine function that you already know. So later we'll be discussing about those functions, but because we cannot utilize the same steps and algorithm we did in chapter 7 anymore, the analysis require us to either go and find the differential equations and solve them accordingly, which would be quite extensive and time consuming, or there is an alternative. The alternative is take the circuit from time domain to frequency domain, resolve the issues in frequency domain, and come back into the time domain. It's like a parallel universe. You go from time to frequency, everything becomes extremely simple, and then you come back. Imagine that you have more than one capacitor, and there is no way you can say that this system is a first degree. Let me give you an example. This system is, for example, you have a capacitor. So far, you had this in your mind, and that there was one R and C. You can say this is only one C. If you happen to have a C in parallel, still you are not worried about it, because two C's in parallel would actually identify for you as one C. What if I have something in between that prevents me from combining the two resistors? Then this is no longer a first degree system. It's going to be a second degree system. So if you have 10 capacitors that no way you can combine them, then it's going to be 10th degree system. What if your incoming signal is not DC? You're in trouble. What if you cannot reduce the system to one capacitor or one inductor? You are in trouble. Of course it's doable, but it would be a lot easier to go into the frequency domain and come back. But you are paying a price for this. If you do the differential equation way, you capture not only the transient analysis, transient response, but you also capture the steady state response. But the engineer says, okay, most of the time I really don't care about the transient response, and I only want a steady state response, because I'm going to let this go for a long time, and that long time could be 10 times 1 millisecond, which is 10 milliseconds. So the 10 millisecond is nothing. Because of that mentality, the transient response is not going to be accessed when you go into the frequency domain. Only a steady state response is going to be utilized. But in order for us to go into the frequency domain, we need to understand how complex numbers are actually going to interact. This is appendix B, I believe, or C of the textbook, or A, doesn't matter. It's an appendix of the textbook. You have access to it. You have seen this before. It's just meant as a simple tutorial to refresh your memory as to what the complex numbers are and how they interact. If I tell you how much is 2 volts, if I have 2 oranges and 5 oranges, how much do I have? I'm going to say 2 oranges and 5 oranges. Then I can say I have 7 oranges. Because the identity of the components I'm talking about is exactly the same, I can actually add them up. If I say 2 milliseconds, and on top of the 2 milliseconds I say 4 milliseconds, what do I get? I get 6 milliseconds, because the units of the two numbers are exactly the same. What if I come in and say you have 5 oranges, but you have 6 apples? What do you say? You can't do anything. You can't add them because they are not summable. If I say, what if you have an amp in one end and volt in another end. When the two components have different units, you need to be able to represent them. In order to represent them, we are going to represent them in the pair. This is the number of apples, this is the number of oranges. This is going to be perhaps current, and this one is going to be perhaps voltages. Because the nature is different, I'm going to present this in a pair. Now, the same thing graphically can be said if you have, this is x-axis and this is y-axis. Now, if I have 2x plus 3x, I can claim 5x. If I have 4y plus 3y, I can claim 7y. But this number is different. If I say this is x1 and y1, what do I mean by this? I mean on x give me x1, on y give me y1, and this one is going to go in, this one is going to come up, it's going to intersect, this is going to be x1 y1. What I just wrote to you is called Cartesian representation of a number. Another way of looking at this is a number in a 2D space. I want to be able to represent this number in a 2D space. Either I can say x1 and y1, or I can also say something else. Why don't I actually attach this number to the origin and tell me the reference of that number, that node, to the origin? This is going to create an angle to the x-axis. I'm going to call this theta 1. And it's going to have a distance from the origin. I'm going to call this rho 1. Rho 1, A1, doesn't matter. It's rho 1. So as soon as I get, first I'm going to rotate theta 1, and then I'm going to go by the amount of rho 1, and I'm going to hit in the same spot. The red representation I just gave you, which is going to be in the form of rho 1 and theta 1, is called polar. This is going to be Cartesian, I hope I have the right spelling, and this one is going to be polar. Obviously, these two are representing the same number, so at some time I would like to be able to convert in, one to another form. In the complex domain, we have to identify units. The unit on the x-axis is going to be 1. So I'm going to say every one of them, this is 1, I'm going to call this 1. And then when I say 2, I mean twice as 1. It could be amp though. And when I say 3, I mean 3 times as 1. So that's the way I see it on the x-axis. When I go on the y-axis, because I have to identify a different type of mentality and unit, I'm going to represent this using a different unit called I. This I is not current. Sometimes you can see it as J actually. Let me call it J. B is better because I don't want you to confuse that with the current we have. So this is J. So when I say you have 1, 2, and 3, this is going to be 3J. My number now is going to be represented as Z as equal to, for example, you have 3x and you have 3y, so it's going to be 3 plus 3j. This is a complex number. J has a definition. J is equal to a square root of -1. I hope everyone remembers that stuff. Now, let's take this to the power of 2. What do we get? J to the power of 2 is going to be -1. Now, you can play with this representation. You can say different things. For example, I can say, take minus to the other end. This is minus J2 as equal to 1. Take J to the underneath. It's going to be minus J as equal to 1 over J. I need you to be able to do this when you get to the complex number. 1 over J is minus J. J2 is going to bring in -1, and if you have another -1 behind it, it's minus is going to give you a 1. So that's one way of looking at it. Now take a look at this and give me a number of possibility. When I say 3 plus 3j, this is 3 unit, this is 3 unit, and 3 unit here, 3 unit there, that's going to take me to the point. Obviously, if this length is the same as this length, it brings memory a special structure in mind. Obviously, you can say theta is going to be 45 degrees. That's what it is. A special triangle. It's going to be a square on this side, 45 degrees, 45 degrees. This length is the same as this length. That's what we have, right? Now, you can use one of the famous equations to find rho 1. Rho 1 is equal to this length to the power of 2, this length to the power of 2. So it's going to be x1 to the power of 2 plus y1 to the power of 2. And all you have to do is a square root of this. So in this case, what do I get? It's going to be a square root of 3 to the power of 2, this one, plus 3 to the power of 2, this one, and it's going to be 9 and 9, 18. That's going to be my rho 1. So I'm going to say that this number can be represented in the following way. Either I can say in blue format, this is 3 and 3j, or in red format, I'm going to say this is going to be a square root of 18 and angle 45 degrees. Okay. Let's go and see if we can change from one domain to another. Let me clean this up. Well, if I know rho 1 and if I know theta 1, can I know x1 and can I know y1? This y1 is the same. So x1 is equal to rho 1 cosine, that's the definition of cosine function, theta 1. y1 is equal to rho 1 sine of theta 1. So if I know rho 1 and theta 1, I would be able to get the Cartesian format. If you take this to the power of 2, what do you get? x1 to the power of 2, you are going to get rho 1 to the power of 2, cosine of theta 1. You don't have to worry about the index. I simply mentioned that for a specific point. y1 to the power of 2 is equal to rho 1 to the power of 2. I'm taking this to the power of 2, sine to the power of 2. If you sum them up, these two, what do you get? x1 to the power of 2 plus y1 to the power of 2 is going to be rho 1. You can factorize rho 1 to the power of 2. You have cosine to the power of 2 theta 1 plus sine to the power of 2 theta 1. And we already know what this is. This is going to be 1. So if this is going to be 1, I'm going to say x1 to the power of 2 plus y1 to the power of 2 is equal to rho 1 to the power of 2. So, if I know x1 and y1, I would know what rho 1 is. Rho 1 is a square root of x1 to the power of 2, y1 to the power of 2. Again, don't worry about the index. I'm just following up consistently from the notation I had. The second question is this. I gave you rho 1 theta 1, you gave me x1 y1. Now I'm going to give you x1 y1, you gave me rho 1. How much is my theta 1? Many people come in and they simply say, if I divide this by this, what do I get? If you divide y1 by x1, you are going to get rho 1 sine of theta 1 divided by rho 1 cosine of theta 1. Okay? Okay, well, it's safe so far. If this is non-zero, you can actually get rid of this. Therefore, y1 divided by x1 is equal to tangent of theta 1. So far, so good. This is fine. This is okay. But people come back and say something that may not be true. You cannot say that theta 1 is equal to tangent inverse of y1 x1. You cannot do that. You can't say this is equal to arctange of y1 divided by x1. That's not true. It's true sometime, it's not true some other time. I want to give you an example. Because I'm dividing this, and because of the nature of the calculator I have in front of me and the way it is built inside, I'm going to miss an opportunity. If this is 1 and 1, when I say 1 divided by 1, if I say this is 1 or 3 by 3, doesn't matter. If this is 3 and this is 3, 3 divided by 3, so I'm going to get 1 tangent of theta is equal to 1, and the only theta that comes to my mind is 45 degrees, right? But you could say that if these are both positive. Let me give you another example. If y1 is minus 3 and x1 is minus 3, what happens? If I say instead of plus 3, it's minus 3 this way, instead of plus 3, it's minus 3 this way, your number is actually going to be here. You can see the line exactly continues, but the number is here. You gave me minus 1 divided by minus 1, you gave me 45 degrees. That's not correct. You need to give me the right angle. The right angle is either this one, or the right angle is this one. Now, you can say that if I have theta 1, all I have to do is to add 180 degrees. You can say if I have theta 1, all I have to do is to reduce 180 degrees. So if I get in this situation, I'm going to subtract or add 180 degrees. Either way is fine. It takes you to the right point. I'm going to summarize that in a moment and tell you what the problem is, and then explain what is the correct response for this. Okay, let me actually go in and give you a different example. I want to maintain this because so is correct. Here is another example. This is x, this is y. I want you to imagine 1 plus minus j. So this is 1. This is minus j, this is coming down, this is the point of the attention, so this is 1 and minus 1, or you can say 1 minus j if you want to put it down in the form of a z. That's the point. Now if I apply this formula on it, what do I get? My y is going to be minus, my x is going to be plus, that's going to be tangent of theta 1, is going to be minus 1, I'm happy. Tangent of theta is equal to minus 1. I can identify what is theta 1 now. Theta 1 is minus 45 degrees, and I'm right on. This is minus 45 degrees. What if the point is actually a mirror point? Right here. This is minus 1, this is plus 1. Still you are going to get the same response. Take a look at this ratio. This time your y is positive, your x is negative. Right? You get the same minus 1, and when you punch it in inside the calculator, it tells you minus 45 degrees. And that's wrong. Because this time you need to actually move either plus 180 degrees or minus 180 degrees to tell me exactly what the angle is. So where is the problem? Where the problem begins? What is the problem? When I say tangent of theta, the calculator is built and the math behind it is made in such a way that all it does, it gives me the angle in the first quarter or the fourth quarter. If I find this, and if I'm in these areas, my arctange is going to work fine. Remember, this is first, second, this is first quarter, second quarter, third quarter, fourth quarter. If you're in the first and the fourth, you're okay. But if you're in the second and the third, you need to do plus minus 180 degrees. Who defines for me if I'm in the second or the third quarter? The only thing I have to watch is x. So if x is negative, plus minus 180 degrees. If x is positive, you're fine. So I'm going to say, I'm going to go in and say, if you have y1 and x1, not only you have to divide and accordingly tell me what is tangent of theta, you need to watch them individually. If x1 is positive, then theta 1 is equal to arctang or tang inverse of y1 x1. If x1 is negative, then you have to actually add or subtract whatever the calculator tells you to do. So this is going to be plus minus, doesn't matter what you do. Either way, it's going to be all right. 180 degrees. One thing keep in mind is this. When you turn off your calculator and you turn it on, by default it is set in degrees. And we have issues with radians. I'm going to explain that in a moment. Radians per second, sometimes we talk about it in the chapter 9. But radians is still a measure of angle for the numbers on 2D space. So if I have rho 1, theta 1, I get x1, y1. That's easy, no trouble, no problem, no headache. If I have x1, y1, I can easily identify rho 1. Rho 1 is always positive. But when I get to the angle, I have to watch this one. If this is positive, I'm fine. If this is negative, I need to have plus minus 180 degrees. Okay. Let's see. Basically, I want to introduce the unity circle. It's a very shortcut into finding the angles. This is x and y, still it's in the 2D space, but I want you to imagine a unit, one unit, and I want you to actually go around and create a circle. So this is a unity circle. This is a very easy circle, and I want everyone to remember this. The length of rho is 1. Obviously, when I go into the y, here still the length is 1, but the point is going to be plus j. So this is plus 1, this is plus j. As I go through this, I'm going to be here, and that's going to be minus 1. The length is still 1. As I continue, this is going to be minus j, and still the length is 1. The length is 1, but it is actually moving around. Plus j, plus 1, minus 1. First, second, third, fourth quarter. If you remember, when I had this in Cartesian mode, I would say z is equal to x1 plus j y1. Allow me to ignore this index 1. I want to make it a lot simpler in that sense. Okay. When I have it in polar domain, z is also shown in a polar form. It's going to be rho e to the power of j theta. Well, if you have any point in the space, generally speaking, as you can see, if this is the point in the space and it has a distance of rho or rho 1, the shadow of this line on the x-axis is rho 1 cosine theta 1. The shadow of this on the y-axis is rho 1 sine of theta 1. So if I wanted to replace this, what do I get? It's going to be rho cosine theta plus j sine theta. This one is going to be rho cosine theta plus j sine theta. Okay? The relationship between this equation and this part is called Euler formula. E to the power of j theta is equal to cosine theta plus j sine theta. If we can verify this, and our appendix actually has shown it, that if I expand this using Taylor expansion, I can see that it is equal to the Taylor expansion of this one. So basically, this one and this one are equal representation of the same point. And I can actually utilize this with the length of rho 1, you see this is 1 and this is 1, and basically relate that to e to the power of j theta. Now, the question, the reason I brought this circle to you is this. What is e to the power of j0? What is e to the power of j90? What is e to the power of j180? And what is e to the power of j270? That's what I'm trying to achieve. E to the power of j0, the amplitude of e to the power of j theta, generally speaking, is 1. So e to the power of j0 is actually pointing it to this point. The amplitude is 1, the angle is 0, so how much is this in real sense? This is going to be equal to 1, this point. When I say e is equal to j90, this is 90. Okay? E to the power of j90, e to the power of j90, 90 degrees, this is going to be plus j. When I say e to the power of j180, 180 is actually this much. That's going to be minus 1. 270 degrees is the same as e to the power of j minus 90 degrees. They are the same. 270 is this part, or minus 90 degrees this part. They reach to the same point. So if that's the case, how much is this? That's minus j. I need you to remember this, because in many occasions, we need you to actually calculate these values. Let me give you an example. If I ask you that a number is basically 5. If I say it's minus 3j, how can you take this to the polar domain? Remember, in the polar domain, rho is always positive. So I have to absorb the negative sign into my angle. When I say minus 5, I mean the minus 1 times 5. It means 5 times minus 1. It means 5 e to the power of j0. When I say minus 3j, minus 3, although it is allowed in terms of Cartesian, it is not allowed in terms of polar. So it's actually 3 times minus j. So this is going to be 3 times e to the power of minus j90 degrees, or 3 times e to the power of j270 degrees. I need you to know what is z in Cartesian, what is z in polar, how we can convert one from to another, or extract one from the other. And also I need you to remember this unity circle, because this unity circle is going to help me to easily take some of the simplest stuff from Cartesian into the polar domain. What is polar domain good for, and what is Cartesian good for? Let's take a look and see which operations we are talking about. Okay. Okay, I'm going to leave that in. If I have z1 as equal to x1 plus jy1, if I have z2 as equal to x2 plus jy2, tell me about the operations. One simple operation is z1 plus z2. And the operations I'm explaining are basically good to understand when you are doing this manually. At some time, I would like you to be able to utilize the calculators, and if you do, you don't have to worry much about these operations. But suppose you forgot to bring in your calculator inside the exam. Summation is easy to do, because I can say this is x1 plus x2 plus j y1 plus y2. Subtraction is easy to do. It's going to be z1 minus z2 as equal to x1 minus x2 plus j y1 minus y2. Division, multiplication are not easy. I want to do the multiplication first. I want to do z multiplied by z2. So x1 plus jy1 times x2 plus jy2. You do this as if you open up the brackets. You remember when you have two brackets and you want to multiply? You do this one at a time. x1, x2, x1, y2. y1, x2, y1, y2. So let's take a look. This one is going to be x1, x2 plus x1, y2, j. I'm fine. Plus x2, y1, j. But I need you now to claim that you understood what I just said a moment ago. J, y1, j, y2. I can say this is y1, y2. But since I'm saying j times j, I'm talking about j to the power of 2. I'm talking about minus 1. This is the one many people forget. Isn't that silly? I want you to be able to remember this. So this is going to be equal to, it's going to be the real part. This is the real part, this is the real part. You can sum up the real parts because they are in the same nature. These two are complex parts. You can sum up the complex parts, but you can't do anything else. So it's x1, x2 minus y1, y2 plus x1, y1 plus x2, y1, x1, y2, x2, y1, j. Real part, imaginary part. Again, remember, this is real part. I might have forgotten about this. Real part. And this is the imaginary part. Okay. The summation and subtraction was perfectly easy to do, but the multiplication I had to do something. The division is actually more challenging. I know it's late in the afternoon, but I would like you to stay focused with me in terms of what to do. I tell you what the mistakes I see sometimes. So let me write it down. Z1 times Z2 as equal to the real part minus, plus the x1 and y2, y1, x2. Okay. When I want to say z1 divided by z2, I don't blame you. Apparently what happens in one of the courses, they come in, they touch the complex number in one session and they go. That's something happened. But on this course, unfortunately, for after the midterm, heavily depends on the complex number. So if you need to go and take a Chang School course on complex number, please do. That's really that important for us. So Z1, it's x1 plus y1j divided by x2 plus y2j. The pitfall I see, this interesting mistake I see is this. People come in and for some strange reason, they think they can separate this. They write this down as, and I want to write it down in the red because that's incorrect, x1, x2 plus j, y1, y2. You can't do this. You can't separate this. This is actually blocking you from doing anything because it's underneath. This is totally unacceptable. Okay? So what is the problem? The problem is x1 divided by this. x1 is real, but this one is z, and they don't communicate the same language. You can't divide apple by orange. I need this to be the same as this one in nature. In order to do that, you may remember we had something called conjugate number. Conjugate number, if you have x1 plus y1j or x2 plus jy2, the complex of z2, which is usually shown by this, is equal to x2 minus y2j. This, whatever it is, this sign is going to change. What is happening? If you happen to have, right? The conjugate of z, what is that? The conjugate of z, for example, x plus y, is actually taking you to the other end. The length is the same, but y is negated. This guy is actually going to reverse itself, the same length, and this is z conjugate. Z conjugate. Why do I need z conjugate? Let's take a look at the reason I want to focus on the z conjugate. Okay, now, if I have a number, and if I multiply this by the conjugate, what do I get? Well, remember the top one, all the x's are going to be multiplied, and then all the y's, you can see yj, yj. It's going to be y2. You have a minus sign. jj is going to give you another minus sign, so it's going to be plus y2. And then you have x minus yj, x plus yj, they cancel each other out. It's real. If I multiply z by z conjugate, z times z conjugate is the same as rho to the power of 2. Absolute value of z to the power of 2, or rho to the power of 2. Rho was the distance from the point to the origin. I hope everybody remembers that. So because of this nature, I have to go through a bit of a challenge. I need to actually multiply x2 plus y2j first into its conjugate, because it turns out to be real. But you can't just go in and do the stuff to the denominator. You have to do the same thing to the numerator. So the numerator is going to be x2 minus y2j. Because you can say these two are going to cancel each other out, right? Okay, I need a space. I'm going to raise this. What is underneath? Underneath now becomes pure real number. And fortunately, it's going to be even positive number. What is on top? The top, you don't have to memorize anything. You simply can actually expand this. x1, x2 is real. Then y1, y2, jj minus 1. You have a minus 1. So it's going to be plus y1, y2. Again, please don't memorize anything. You are supposed to remember all of that. This one then is going to be plus, you have a j, x2, y1, minus y2, x1. Why? Because now I can separate this. Now I can say real divided by the real, plus j real divided by the real. Then I'm going to have a piece in terms of how my z is going to be. My zt is going to be this segment plus j this segment. Now I can separate my fraction. That's what happens. Then I have a nice Cartesian form of the division. The interesting thing is this. Although this is quite challenging to do in Cartesian, it is actually a lot easier to do in polar domain. Let's take a look at the polar division and multiplication. Then I'm going to tell you what is going to be a challenge in terms of plus and minus for polar domain. So let me erase this. Okay. If I have z1 as equal to rho 1 e to the power of j theta 1 and z2 as equal to rho 2 e to the power of j theta 2, what can I do in terms of multiplication? Multiplication, z1 times z2. You have rho 1 e j theta 1 times rho 2 e j theta 2. Okay. Rho 1, they are just nice little real numbers. So it's going to be rho 1 times rho 2. This is e to the sum, And basically, you just have the base the same. E and E are the same. All you have to do is to add up the power. So it's going to be j theta 1 plus theta 2. Wasn't this a lot easier than the multiplication I just showed you in Cartesian mode? Let me surprise you with the division. Z1 divided by Z2, what is this? This is rho 1 e to the power of j theta 1 divided by rho 2 e to the power of j theta 2. What do I get? Rho 1 divided by rho 1, actually, very immediate, you can say this is going to be rho 1 divided by rho 2 times e to the power of j theta 1 minus theta 2. If you are making a mistake at this stage on these complex operations or any similar operations, then you are weak in terms of math. As soon as you identify that, you should be able to go back and fix this. E, the base is the same, J subtraction. Now that is a lot easier than this. This is a lot easier than the multiplication I showed you. But can you tell me if the summation of the polar domain is easy? If you want to add this and this, what can you do? Let me show you. Rho 1 e to the power of j theta 1 plus rho 2 e to the power of j theta 2. You really cannot do anything. There is nothing you can do with this. You can't say it's rho 1 plus rho 2. You can't say it's theta 1 plus theta 2. There is nothing you can do. So here is the simple rule of thumb. The rule of thumb says is this. If you have complex numbers and you want to add them in Cartesian. If you have complex numbers and you want to do multiplication and division, do that in polar domain. If you have Cartesian and you want to do multiplication, do the conversion into the polar domain, multiply, then return back once again to the Cartesian mode. The good news is the approved calculators allow you to actually take in Cartesian, do the multiplications and divisions and all that. To take in the polar, do the summations and subtractions and all that without lifting a finger. Of course you lift a finger, but that's what it is. So this is the fundamental. You need to understand what the fundamental is. But in terms of operation, obviously we are going to show you sometime later how to use calculator to achieve the calculation, multiplication and summation and subtraction. Now, by now, I have covered the important materials for the complex operations. There are other operations we would be talking about on Wednesday, for example, how to add sine and cosine functions together. And for that, I need everyone to know how to do the calculations in complex domain. For now, I thank you very much for listening, and I hope to see you on Wednesday. Thank you.